Hi, and welcome to our next lesson, optimization problems. What we're looking at in an optimization problem is we're looking at a problem which we're interested in finding out where a particular function is going to be at its maximum or at its minimum. And since we've been spending quite a bit of time looking at where to find maximums and minimums in functions, this would be pretty easy except for the fact we don't have an equation. So our first job, and frankly our most challenging job of any of these problems, is always going to be to find out what the equation is. Thankfully, we do have a number of steps that we can follow to kind of help us out. And our first step is going to be, I'll write it down over here, is what to optimize. Always make sure as you read through the question that you take a look at what is it in the question you want to optimize. What is it in the question that you want to find a maximum or a minimum of? Well, let's read the question here. A rectangular animal pen is to be constructed out of 80 meters of fencing. The pen is to be enclosed on all four sides. An additional fence is to be added that splits the rectangular pen into two sections, with one of those two sections being a square. What dimensions will maximize the area of the pen? And there it is, right there at the end. We want to maximize the area of the pen. So now that we know that it's area that we're interested in finding the maximum of, our next step is going to be to come up with a function that represents this area. So step number 2 is to generate the function. Well, it's an area of a rectangle, so that seems easy enough. Area, of course, of a rectangle is the length of the rectangle times the width of the rectangle. Unfortunately, right now, that's not really too helpful for us because, that's kind of just a generic formula. We need a more specific formula for this problem. Moreover, we want a formula that has only a single variable in it so we can do our analysis with a little bit of calculus. What I always find really helps for me in any kind of question that I could draw a diagram is to draw a diagram. And here, of course, we're talking about rectangles and pens and squares and stuff, so I'm going to be right away drawing a diagram. We have a rectangular pen. There we go. I can draw a rectangle. Okay. And then we're going to put in an additional fence that will split this into two, but one of those two extra pens are going to be a square. So I'll draw this so it sort of looks right. There we go. So this one on the left here is my square. Oh, it doesn't want me to close it off. Okay, fine. And what we need to do now is introduce another variable. We'll use our old friend x. Everybody's familiar with x, though of course you could use other variables as well. We have lots of sections of fence here. We could let any of them be an x if we wanted to, but we should be a little bit smart about this. The pen on the left is a square, excuse me, so why not represent all of these guys with x's? And in fact, while we're at it, this one over here, because this is a rectangle, would also be an x. So there we go. We've actually got five of the sections of fences being represented with a variable now. We have two that are missing, this one in here and this one over here. We know that these two got to be the same. It's tempting to sort of throw in another variable like a y or something, but that actually doesn't really help us out. So I'm going to resist that option. I want to keep looking at using just a single variable for this. So what I need to do is read through the question and look for some other information. And there is some other information that we haven't taken advantage of yet. We have 80 meters of fencing all together. So all these section of fences have to add up to 80. Okay, well, so far I have 5 sections of fences being represented by an x, so that's 5x. So if I take my 80 meters of fencing and subtract off the 5 x's that I have so far, that's how much fence I have left over for the 2 sections I'm missing. Since those 2 sections have to be the same, they must each be just this divided by 2. So now I have an expression to represent these missing sections. This is 80 minus 5x over 2, and of course this one down here is also 80 minus 5x over 2. Now the area of this thing is the length times the width. Well, again, that's not so bad. I can see right here, here's the width, right there. The width is just the x. That's easy enough. The length is this distance right across here. The length is going to be these 2 sections added together, the x plus the 80 minus 5x over 2. We'll simplify this a little bit. Let's see here. Well, Well, 80 divided by 2 is simple enough. That's 45 divided by 2. I'm just going to write 5 halves. If you want to go with decimals, that's fine. We'll simplify this a little bit. We get a 40, and then we have x minus 5 halves, or 1 minus 5 halves. 1, of course, is 2 halves minus 5 halves. That's negative 3 halves x. All right, so there we go. We can now write ourselves an equation. Let's move this guy out. Actually, let's extend the page up a little bit. That'll be easier. Area is length times width, so the area is going to be the length, which is, well, this 40 minus 3 halves x, times the width, which is also an x. So here we go. Now we've got our equation for area. We generated our function. That, as I mentioned at the beginning, is the hardest part of this problem. After this, things get a lot easier. All I got to do is find out where is this going to be at its maximum or at its minimum. And we know that functions are at their maximum or minimum when the first derivative is equal to 0. So all I got to do for my third and final step in this is set the first derivative to 0. All right. So let's take the first derivative of this thing. I think it'd be easier if we multiplied out these brackets before taking the derivative. So I'm going to get 40x minus 3 halves x squared. Taking our first derivative, derivative of 40x, of course, is 40. Derivative of negative 3 halves x squared would be negative 3x. We want to set that equal to 0 and solve for the x. Well, that's not too bad. Take the 40 over to the other side, divide by the negative 3, and we're going to get that the x is 40 thirds. Okay, we're almost there. We have to make sure, though, that we answer the problem. The question wasn't what's the value of x. In fact, there's no mention of an x in this problem at all. The question was, what will be the maximum area? So I need to answer that question. Thankfully, I do have an equation for area. It's sitting right here. And it's got an x in it. Now that I know what the x is, all I have to do is substitute it. In fact, I think I'm going to use the one below it. I think that one's a little simpler to use. Let's draw a little line here. So our area is simply going to be, let's see, 40 times the x, which is 40 thirds, minus 3 halves times 40 thirds squared. And at this point, of course, I'm going to push this through my calculator, and I get approximately about 267. And since this was all measured in meters and this is area, this would be 267 square meters. So let's answer the question. The maximum area is about 267 square meters. Actually, we do know a little bit more than that. We actually know the dimensions of this field that gives us this maximum area. For instance, we figured out the x is 40 thirds, which is about, what, that 13.3? Is that right? No, 13.7. Oh, boy. No, 13.3. I was right the first time. About 13.3 meters. That's got to be the width. Length, we have an expression for length. We could substitute that 40 thirds into that, figure out what the length is. Question didn't ask for it, but I could easily figure it out. Sometimes questions do ask for those things, so be on the lookout for that. But for this one, we are done. We'll take another problem in class, so we'll see you then.